the Collatz Conjecture. It's a fun little math game that I personally never played when I was a lad. It kind of reminds me of the Ackermann function, or John Horton Conway's Game of Life, as an example of how a few simple rules can lead to a surprisingly wide array of mathematical results, though arguably probably not as visually pleasing as Conway's Game of Life. So here's the way the game works. You start with a number, a positive integer, greater than 1. If the number is even, you divide it by 2, and if the number is odd, you multiply it by 3 and then add 1. The order here is very important, so don't forget your "pretty please, my dear Aunt Sally." So if you get 5, your answer should not be 18, but rather 16. You do the 3n part first, then add 1. A very popular number to test out the Collatz Conjecture with is 27, because it reaches a high of 9,232 before falling back down to 1. And here are some other numbers with a high of 9,232. And if you don't count the first number, here's some other numbers with a high of 9,232. It doesn't work once you get past 2 times 9,232. But there's something about this number of 9,232. Are there other sequences that feature the number 9,232? Lots of them do. So 27 falls down to 1 after 111 steps. Are there other sequences of 111 steps that don't have the number 9,232 in them? A few, actually. And on the questions go. Now here's a cool thing that I swear I just stumbled upon by accident, because yes, even my stuffy old math teacher liked the occasional thing that was cool. He would erase the board too fast, of course, so I wasn't always able to write down where it was. But we'll save that for another time. So this is kind of like how in Conway's Game of Life, you've got stable colonies, you've got repeaters, and you've got gliders. But then there are some depressing patterns like this one that just slowly die out. Well, this is half like that. So let's say you've got 10 nines in a row. So that's what, 10 billion minus 1. Now, we run it through our Collatz machine, and see, the 9s slowly get eaten up, and then they're all gone, and you're left with this bigger number, which then counts down to 1. So what happens with 20 9s in a row? Same situation.
Same thing.
The 9s get eaten up, and if you look at the digits that get left behind, they're more or less the same. Now, the Collatz Conjecture has been tested by actual professionals on all numbers up to 2 to the 68th power, which is a number of about 22, 23 digits. So why don't we give this thing a real test and try a number of 1 million 9s in a row. Turn the page. Well, here was all the data I thought to keep track of. As you can see, after the 1 million 9s get processed, so to speak, we end up with a number that swells up to 1.1 million digits in size. And despite this advantage, in the long run, the house always wins. And after just over 30 million applications of the 2 Collatz rules, our big number falls back down to 1. Consecutive up and down means the number is multiplied by 3, add 1, then divided by 2, then multiplied by 3 again, then divided by 2 again, and this happens 44 times in a row. That's the second highest number, next to what it starts out with, 2 million, or twice the number of 9s we had in our number. The 3n plus 1 rule can only be applied once at a time, but we can divide by 2 as much as we like, and at some point near the end of the sequence it happened 26 times in a row. And this seems to be one of the reasons we haven't yet seen a number that just keeps rising to infinity. But this only took me 81 hours, which is not very long. So now, let's try 10 million 9s in a row. Whew, well, that took some doing, but we finally made it to the summit. And as predicted, try not to be too smug about it, we start with 2 times the number of 9s of consecutive ups and downs, this time 20 million. And now we're stuck with a number that's 11.7 million digits long. Now let's see how long it takes to fall back to 1. This might take a while, so we'll get back to it later. The Collatz Conjecture, according to Wikipedia, is also known by a couple other names, such as the 3n plus 1 problem, the 3n plus 1 conjecture, the Ulam conjecture after Stanislaw Ulam, Kakutani's problem after Shizuo Kakutani, the Thwaites conjecture after Sir Brian Thwaites, Hasse's algorithm after Helmut Hasse, or the Syracuse problem, which is strange because I always thought that this was the Syracuse problem.
Come on, hurry up. We're waiting for you to read.
Don't rush me. Rome wasn't built in a day, neither was Syracuse.
Thank you, Professor Schempp. During the Cold War, it was also called a Russian conspiracy to decrease American productivity. Such is the fascination with this problem. No wonder so many people want to take credit for it. So the big question or conjecture is there a number that you can plug into it that doesn't eventually fall back down to 1? As I said before, study of the Collatz Conjecture leads to some interesting results just before driving you completely insane. For me, one of the most interesting is that so many numbers in a row tend to have the same number of steps. In my own brief searchings, my own record is 310 numbers in a row, starting with 6,622,073,000 that all end after 211 steps. And there seems to be no rhyme or reason to it. The similarities between 6,622,073,305 and 6,622,073,306 begin at step 14, while the similarities between 6,622,073,306 and 6,622,073,307 begin at step 194. In its own way, it's a perfect numerical system. You divide an even number by 2 until it becomes odd, and when it's odd, you multiply it by 3, which gives you an odd number, so you add the 1 to make it even. And when it's a 1, you stop. A strange mix of simplicity, combined with the unpredictability of the results, making it the perfect unsolved math problem. It lends itself quite readily to a computer program. In fact, why don't we try that right now? Time for a brief lesson in the Java programming language. I'll try to keep it short, I promise. We'll just skip the first 2 lines. That's just some Java boilerplate. This system out print line command tells the computer to print out something for the benefit of us mere humans. Now, the long here refers to what we programmers call a variable. A variable. If we want to play with numbers in a Java computer program, we have to use a placeholder called a variable, which will hold a number for us, and we can manipulate it as we wish. But we have to be very specific about what we want. This is Java, after all, not JavaScript. If we want to work with integers, we use either an integer or an int, or in this case, a long, which is just a slightly bigger integer, which will mostly work for our purposes here. If you really want to explore the Collatz Conjecture, you might have to risk using a big integer. For the purposes of illustration, we'll just stick with a long for now. This gobbledygook here means we will take a number entered in by the user and use it to run the Collatz program to see what results we get. We print out the number here just in case. Now, normally you'd use what's called a for loop for a simple program like this, but we don't know how many times we'll have to apply the 2 rules, so we use the while command to signify a loop that continues until a certain condition is met. In this case, while our number is greater than 1, we keep going, and then it's just the code version of the 2 rules. This percentage sign gives you the remainder of a division, and an even number divided by 2 gives you a remainder of 0, so we divide it by 2. Otherwise, or else, we multiply it by 3 and add a 1, and then go back to the while condition to see if the number is a 1 yet. And that's it. It's what computers do best. Lots of boring tasks, really accurately, pretty fast. Now, normally with a program like this, you'd have to include a few lines like this to make sure the number doesn't fall out of bounds and cause an error. Or if you want to turn this into a web app, you'll need to have a bit of code like this try-catch statement to make sure the user doesn't try to cheat the system and enter an illegal input. Whole industries have flourished because of the user input problem. But that's one of the wonderful, magical things about the Collatz Conjecture. As long as you only use an integer of 1 or higher, this line of code is not necessary at all. So the next question is, well, is there a chance for a number to somehow accidentally fall through the safety net created by our 2 rules? Well, First of all, let me take a moment to actually state the Collatz Conjecture. The Collatz Conjecture states that if you apply these two rules over and over again, every integer 1 or greater will eventually fall back down to 1. If you think of the numbers in terms of directions, every integer bigger than 1 will eventually turn into 1 after applying the two rules as many times as necessary. So we've had some fun with the Collatz Conjecture, so now let's attempt to build our proof. And let's start here by asking, is there a chance for a number to somehow fall through and get past 1? We can try to answer this question by building something like an Eratosthenes sieve, but not for prime numbers. So we've got our two numbers, and we start with 1. Then we cross off 2, 4, 8, 16, 32, and all of the other powers of 2. So this is the main thread, the last one just before you finish your run with the Collatz Conjecture. So what's next? 3. So we cross off 3, 6, 12, 24, 48, and all the other powers of 2 associated with 3. So what's next? 5. So we cross off 5, 10, 20, 40, 80. And this one's interesting because it's kind of like our main thread, but times 10. In fact, 5 goes to 16, then 8, 4, 2, 1. So this is the second to last thread before you're done. So what's next? 7. So we go 7, 14, 28, 15, 6, 56, 112, and on and on. So by now, if you've taken an SAT or an ACT test, you should start to see a pattern. Every odd number has this pattern of powers of 2 rising above it like a skyscraper. Speaking of prime numbers, is there any connection between the Collatz Conjecture and the prime numbers? Well, thankfully, not really, because it only matters if a number is odd or even. It doesn't matter how odd a number is. But there is something about that 2n rule. I mean, if you try to change that, things just fall apart quickly. For example, what if it's 3n? Well, that's all well and good, but what about all those other numbers? What can you do with them? Multiplied by 5040? Each number would need its own rule, or even if it was a nice even 4n, you still have a bunch of numbers that need their own rules. So, we'll just stick with 2 rules and 2n as the rule. But say you were trying to figure out if a number is prime or not. Take a number like 1200, for example. How do you start? Well, you start by dividing by 2, and then by 3, and so on. Very quickly you realize that 1200 is really, really not a prime. And you know that because it's divisible by 2. In fact, isn't there some rule about how all whole numbers are just a series of primes? What's that called again? It's the fundamental theorem of arithmetic! It's fundamental! This is serving as or being an essential part of a foundation of basis! It's fundamental! And here it is in a book, not just something on the internet. Remember books? Wow. Me neither. It's been a while. I guess the fundamental theorem of arithmetic is just one of those things you only have on your 5th grade math final, and then you never have to think about it again. That's kind of nice. Now, normally when you're illustrating the Collatz Conjecture, you do it in a nice, pretty tree formation. But let's take some, maybe all of the fun out of it. And we'll have this grid-like way of looking at the numbers. Think of it like directed graphs, or like something I learned about 25 years ago in one of my favorite classes, discrete mathematics. And they were called deterministic automata, except when we were learning about it, we were using them to show that certain strings of letters either belonged or didn't belong to a very basic grammar. Here, we're creating the ultimate deterministic automata, containing all the infinite positive integers and our 2 Collatz rules. So we can start with our 3n plus 1 rule, because at the bottom of all these stacks are our odd numbers, and they all point to a different stack. So, all you have to do to show that the Collatz Conjecture is true is find a way to show that all these stacks point to each other, and that you eventually, no matter where you are in this infinite game of chutes and ladders, you will eventually get to the main stack, or the 1 stack. So how on earth can we possibly do that? Well, I'm afraid we're going to need a second boring lesson here. I know. I'm sorry.
Stay with me on this. The sooner you face it, the better off you're going to be.
Thank you for having my back, George. It's time for a lesson in division and what are called remainders, or modulo. specifically a modulo operation, which is a fancy term for remainders. Because in my explorations of the Collatz conjecture, I noticed something kind of peculiar. Take the number 27 again, for example. We'll run it through the usual process, but instead of each number, we'll look at the modulo of 3 for each number. So each number is divided by 3, and we look at its remainder. Okay, that's not a good example. Let's try something like 221,184 instead. As you can see, we start with zeros, but then it alternates between ones and twos. And sometimes you'll get 2 ones in a row, but never 2 twos in a row. Now, in mathematics, for statements that have been proved, the theorem is the highest you can get, and it's ultimately the thing to strive for. But conjectures are pretty good too. They're basically theorems that haven't been proved. Statements of lesser importance are called lemmas, propositions, or corollaries. So I'm going to make some propositions right here. Here goes. Wish me luck. Proposition 1. In the Collatz conjecture, a number divided by 3 can start out with a remainder of 0, but will ultimately end up with a remainder of either 1 or 2. Proposition 2. In a Collatz sequence of just the remainders of the numbers 1 divided by 3, you will never get 2 twos in a row. Let's start with Proposition 1. Now, we've got our stacks of 3, 9, and 15. Now, if you start to go through and look at all the numbers, you'll soon realize that no matter how many times you multiply these numbers by 2, they are all perfectly divisible by 3. So they all have the remainder of 0. So you can only start a Collatz sequence with any of these numbers because there's no chance of jumping to one of them with an application of the 3n plus 1 rule. Now, Proposition 2 is a little trickier, so let's look at dividing by 3 some more. Now, numbers like 0, 3, 6, 9, etc. to infinity are all evenly divisible by 3, and their remainder, or modulo, is all 0. Now, if you divide 1 by 3, its modulo is 1. If you divide 2 by 3, its modulo is 2. So 1 divided by 3, or 4, or 7, 10, 13, to infinity, all have a modulo of 1. And 2, and 5, 8, 11, 14, to infinity, all have a modulo of 2. Now, how does multiplication affect the modulo? We start with 1, modulo of 1. Multiply by 2, we get 2, and a modulo of 2. Multiply by 2, we get 4, modulo of 1. Multiply by 2 again, we get 8, and a modulo of 2, and on to infinity. So the modulo will always fluctuate between 1 and 2 like this. And another way to look at it is through the mind-blowing lens of base 3. Now, what is base? Well, base is a fancy way of saying the concept of digits. For example, what we commonly use every day is base 10, because we use the digits 0 through 9. So 12:30 p.m., the bottle of ketchup is 680 grams, the show 2.5 Men. These are all base 10. Now, programmers used to have to think about bases like binary or 2, which is just 0 and 1 for all numbers, or a base like 16 or hexadecimal to allocate memory for a program, probably in machine language, but that was the old days, and thank God they're all but gone. Now, for 3, here is a 1 in base 10, and it's the same in base 3. Multiply 1 by 2 and we get 2. Here's 2 in base 10 and 2 in base 3. Multiply again and we get 4. Here's 4 in base 10, but in base 3, it looks like an 11. Multiply again by 2 and we get 8. Here's 8 in base 10, but in base 3, it's 22. Multiply again by 2 and we get 16, and 16 in base 10 is normal, but 16 in base 3 is 121. Now, if you just look at the ones digits in the base 3 numbers, you will see again that we alternate between 1 and 2. So why don't we get 2 twos in a row? And why do we occasionally get 2 ones in a row? Well, the first 1 is an odd number, and the second one is where the number gets multiplied by 3. Now, no matter what integer we multiply by 3, we will get a number, when divided by 3, that has a remainder of 0. We add the plus 1, and suddenly the number has a remainder of 1. The plus 1 will never give us a remainder of 2, so therefore we will never get 2 twos in a row. QED. Well, that's a bit of a start, but how do we actually prove the Collatz conjecture? Well, one way to do it is to find what mathematicians call a counterexample. A counterexample, and we have two choices. One, either a number that rises to infinity forever, or two, a number that doesn't fall into the 4-2-1 loop. Because even though we stop at 1, technically you can go on forever, because in 3n plus 1, if n is a 1, you get 4. And so you can go 4, 2, 1, and back to 4 again forever. So what would a counterexample even look like if we could find one? Well, once again, I will slightly bend the rules and take a look at the negative numbers, because, believe it or not, the two rules of 2n and 3n plus 1 do work on the negative numbers. Unfortunately, the proof down there becomes a little more complicated, because instead of a 4-2-1 loop, now we've got 3 loops. And we can use our stack structures to illustrate them like this. Now, this one here is interesting because it's just -1 and -2. Well, what happens to -4? -4 becomes -2, and when you apply the 3n plus 1 to -1, it becomes -3. But because of the rules of addition, the plus 1 raises it to -2. So one thing we can do is change the rule from 3n plus 1 to 3n minus 1. Then suddenly these 3 loops are on the positive side. And we can now ask, well, let's look at a number like -27. What happens? Well, it's a sequence of 111, and it drops all the way to -9,232, and eventually rises back up to -1. But how many other sequences have a low of -9,232? And how... Oh, well, we'll save that for another time. Getting deja vu here. But this brings up another interesting thing about Collatz. As it turns out, the +1 of 3n plus 1 is a lot more influential than it first appears, which leads me to my next proposition. Proposition 3. Using the more general 3n plus x. If x is a positive odd integer, there will be a loop of length 3 at 4x, 2x, and x. And there will be a loop of length 2 at -2x and -x. So what does this mean? Well, let's start with an x of 1. So the loop is 4, 2, 1. And you can try this at home yourself. You'll just have to write the program yourself. Sorry. But let's say the rule is 3n plus 3n. By God, there it is. 3, 6, and 12. It's kind of like how in algebra you learn about parabolas, and then you have to spend about half a chapter on how they can be placed at places other than 0, 0 in a Cartesian plane. Thankfully, in the Collatz universe, we don't have to square any numbers or, God forbid, find their square square roots. Now, let's take a look at something ridiculous like 3n plus 1001. Okay, it's got the traditional 1001, 2002, and 4004 we expect, but what about all this other stuff? I didn't sign up for this. Well, looks like we got to change the conjecture a little bit and say if the rules are 2n and 3n plus 1001, any number 1 or greater is going to end up in one of these 29 loops. And do we really know that there are only 29? Could there be more? I don't think so, because I used a brute force approach to check all the numbers up to 4 million, but in the meantime we can attempt to illustrate as best we can what a couple of these loops will look like. But let's leave all that aside for now, because now it's time to tinker with the 3 part of 3n plus 1. Well, first of all, what happens when it's 6n plus 2? Thankfully, quite similar to 3n plus 1, it just gets there either a little faster or a little slower. But I'll leave that for others to explore for now. Like I said earlier, lots of interesting questions. First, let's go the other way and see what happens when 3n plus 1 is 0n plus 1. If I remember correctly, if you're doing an inductive proof, this would normally be called a base case. Anyway, we go back to our stacks and we find that this one is the easiest to prove. Well, why can't 3n plus 1 be like this? As you can see, all odd numbers at the bottom of the stacks, when multiplied by 0, become 0. We add 1 and boom. We go straight to 1 and we're done. Oh man, that rhymed. Even 1 itself has a loop of length 1 back onto itself. We have shown that all the stacks are connected, all numbers lead to 1, therefore 0n plus 1 is true. Now, 1n plus 1, and we're back more or less to where we were, but it's a little bit simpler. 3 goes to 4, 4 goes to 2, 2 goes to 1, and 1 only goes up to 2, so it's a lot simpler. There's not as much guesswork about where any odd number is going to go. And if we take every other number in this list, we can see that there will always be at least one number pointing to an odd number stack. 5 goes to 3, 9 goes to 5, 13 goes to 7, 17 goes to 9, and on to infinity we go. So, if we put this in more mathematical terms, it might look like this. For all n, where n is a member of the positive integers, or in mathematical lingo, z+, and n is odd and greater than 1, then the number 2n minus 1 points to the n stack. Therefore, 1n plus 1 is true, because every number eventually falls to 1. Now, 2n plus 2, and remember the plus 1 has to be even when the coefficient of n is even. Otherwise, we'll always have an odd number, and we'll be stuck in a loop forever, which we don't want. Anyway, we actually see the same pattern as with 1n plus 1. The only difference is that because the formula is twice as much, a given odd number will point a little bit higher up the stack than 1n plus 1. But they ultimately end up pointing to the same stacks. So 5 goes to 3, 9 goes to 5, 13 goes to 7, 17 goes to 9, and on to infinity. Therefore, every stack is covered. Every number eventually falls to 1, so 2n plus 2 is true. Now we finally come to 3n plus 1, but the pattern is a little more subtle. We have 3 cases to consider here. The first case is where 3 points to 5, 7 points to 11, 11 points to 17, 15 points to 23, and on to infinity. In mathematical terms, we would say for all n, where n is a member of z+, and n mod 6 equals 5, 2/3 of n plus 1 minus 1 points to n. I think that works. It works. So that covers 1/3 of all numbers. Next, we consider the case where n mod 6 equals 1. So we have 9 points to 7, 17 points to 13, 25 points to 19, and on. In mathematical terms, we would say, for all n, where n is a member of z+, and n mod 6 equals 1, 4/3 of n minus 1, plus 1 points to n. I think that works. It works. The last case is all those numbers where n mod 6 equals 3, or n mod 3 equals 0. All those pesky numbers perfectly divisible by 3. Well, as we've shown before in these stacks, these are all the numbers that can start a Collatz sequence but can't end it. But the bottom number of the stack points to some other stack, so really these are just redundancies that bolster the system in a way. So 3 points to 10, or the 5 stack, 9 points to 28, or the 7 stack, 15 points to 23, 21 points to 31, 64, 27 points to 41, 33 points to 25, 39 points to 59. Unfortunately, there's no simple formula this time, but we've shown that the numbers of n mod 6 equals 3 all point to a stack. We've therefore covered all the cases we need to show that all the stacks are connected, and that any number chosen will eventually fall down to 1. But what about something like 3n plus 1001? Well, ultimately, I think the lesson we can take from this is that we're not dealing with an ordinary case of points and vectors or a normal deterministic automata. When combined with numbers and arithmetic, you're going to get some strange results. But I think that no matter what number of loops you have for whatever placement for plus 1 you choose, the resulting loops will be close to 0 rather than found in the far reaches of infinity. I don't know if there's a mathematical term for that. In astronomy, for example, the local group is just our Milky Way and the Andromeda Galaxy. So for 3n plus 1001, it's probably just these 22 loops that are close by, as well as these 7 on the negative side. And for 3n plus 1, it's just the one loop on the positive side and 3 on the negative side, governing the whole infinity of integers. Another way of looking at it is to use the counterexample strategy to ask, well, suppose a number does exist that doesn't fall back down to 1. What properties would it have to have? It would have to be a number that's neither odd nor even, nor have a remainder of 0, 1, or 2 when divided by 3. But there are no positive integers like that, therefore the Collatz conjecture is true. No? Okay, well, it's worth a try. Okay, so we've seen a number stuck in a loop other than 4, 2, 1. But how about a number that just keeps rising to infinity? Well, let's change 3n plus 1 to something completely random like 4n plus 2. And let's try it on the number 3. Now, fans of old-school binary computer programming just might recognize these numbers. Or to put that in terms of powers of 2, so there we have it. Almost right away we have a number that will alternate between each rule only once and steadily march its way towards infinity. In our paradigm of stacks and arrows, the arrows simply change direction, heading away from 1 in the lower left-hand corner. And after a preliminary look, it seems that with anything above 3n plus 1, numbers that head to infinity are the rule rather than the exception, and because we don't change the 2n rule, any power of 2 will still fall down to 1. And so far in my meager searchings, 5n plus 1 and 10n plus 2 are the only places out of 30n where we see other numbers that loop, that don't include the number 1. So if the rules are 5n plus 1 and we pick 13, we get this. Similarly, if the rules are 10n plus 2 and we pick 13, we get this. What? Okay, I found another 5n plus 1 example. 17. So we get another cycle of 10 like this. And just for good measure, when the rule is 5n plus 1 and n is 1, we get the following loop of 7. I very nearly forgot. Well, it took some doing, but with my non-Alienware computer, I finally finished the big 10 million digit Collatz number. And after just over 290 million iterations, our giant number made its way back down to 1. And for some reason, the number 26 seems to be the lucky number in terms of the number of times in a row that the 2n rule can be applied. But, that thing can be inflated easily enough. All you got to do is try a number like 2 to the 27th power or the 28th, that kind of thing. I probably forgot something else. There's 2 things I'm supposed to remind you to do. Oh well, it'll come to me later. All right, well, that's about all the damage I can do for right now, and as always, thank you for watching.
Well, thank you very much.
Goodbye now. I beg your pardon?
I said goodbye now.
Goodbye now. There's no sense to that. Obviously it's now. I mean, you wouldn't say goodbye tomorrow or goodbye 2 hours ago.
You've got hold of something there, brother.
I've got hold of some... I haven't got hold of anything.
There, hold it, hold it. Ain't it aggravating? Well, goodbye now.
Multiplicative persistence. This is a very silly number game that I definitely didn't play as a child. Here's how it works. You take a not very randomly chosen number like that one. So what you do is you take the individual digits of the number, multiply them together, and you get a new number. Incidentally, this means that any combination or permutation of the digits of the first number will give you the same result. Also, you can have as many ones as you like, and it won't make a difference. But if you have even 1 0, well, the whole number goes to 0, and it's game over. The game ends more generally when you get down to a 1-digit number. You see what I mean? Silly. But now that we're living in the age of internet-based video games that you can apparently play forever, it is kind of nice to have something finite for a change. Now, this number is special because it represents the longest sequence that can be played with this game, and apparently the search is actually on to find a sequence that's even longer. One hasn't been found yet, and no one knows why. But what happens when we look at just these numbers? What do all these numbers have in common? I wonder. I really, really wonder.
Yeah!